examples and tell you that these are the canonical examples, and more complicated versions of it exist, but this is the simplest, frankly. Now, these are bifurcations which involve basically one variable. So, it's of the form x dot equal to f of x, and along with x, there's a parameter mu, say. And this function, this vector field f, has a parameter or constant sitting there, mu, and a bifurcation occurs if at some critical value of mu, you cross over from one kind of dynamical behavior to another kind of dynamical behavior, in a manner which will become clear. Now, mu could itself be a set of parameters, more than one. It could be a collection of parameters, and the number of parameters you need which take part in the bifurcation is called the codimension of the bifurcation, whereas the dimension of the phase space is that of x, from 1 to capital N. Now, I'm going to illustrate this for codimension 1, namely only one parameter here, a single scalar parameter, and we look at it in terms of examples where this x vector itself is essentially one-dimensional. But just to get you, just to make it a little familiar, because we're used to problems in mechanics, I'll make it two-dimensional with one of the variables playing no role at all, essentially. So this is the problem of a particle moving on the x-axis in a given potential, v of x. So the equations of motion then look like this. X dot is p. I'll set the mass of this particle equal to 1. So it's x dot equal to p, and p dot equal to the force. Now this force comes from some potential. And suppose the force has this form, and this is the simplest of the law. It's of the form mu minus x squared. So now at the back of our minds, we have in mind the fact that v of x, this is the force, so it's minus v prime of x. So let's integrate it. It's equal to minus mu x plus x cubed over 3. So that's the potential, and this here is the force, and that's your dynamical system. So the critical points clearly are at p equal to 0, this must be 0, and mu equal to x squared, which of course has no roots if mu is negative, but has roots, two roots, plus or minus square root of mu, if mu is positive, and that's how the bifurcation occurs. Okay. Instead of writing that, let me draw the picture for v, and you'll see immediately what happens. So we need three pictures: mu less than 0, mu equal to 0, and mu greater than 0. And these are pictures of x versus the potential v of x. For mu less than 0, this is a positive slope near the origin, and this is x cubed, which diverges as x goes to infinity. So this curve obviously looks like this, with the slope here equal to mod mu. Okay. At mu equal to 0, this disappears, and you have an inflection point. And mu greater than 0, this guy has a negative slope at the origin, but then the x cubed term dominates as x increases, so therefore it looks like this. The potential looks like this. Now it's immediately clear what's happening. For mu less than 0, there's no equilibrium point. For mu equal to 0, there's a marginal equilibrium point. And for mu greater than 0, there's an unstable equilibrium point and a stable equilibrium point here. This is at minus square root of mu, and this fellow is at plus square root. The negative root is unstable, the positive root is stable. So we are ready to draw the bifurcation diagram, which is a graph of the equilibrium points. It should involve, as a function of mu, it should involve p, x, and mu, but p is always 0. So we can just as well work on the plane x, and this is at the equilibrium point, x critical point. For mu less than 0, nothing. And for mu greater than 0, there's a critical point at plus root mu and minus root mu. This guy is stable and that guy is unstable, being a minimum of the potential and a maximum of the potential. And it's parabolic because square root of mu curve goes like this, and this fellow goes like this. This is the unstable root. And it's easy to linearize these equations about the critical point and discover that this point here is a stable equilibrium point, a stable node, asymptotically stable node, and this is an unstable node. So, this is a saddle point. So this is a saddle node bifurcation. This thing here is a picture of a saddle node. Notice that at the value mu equal to 0, at this value precisely, this equation is not linearizable because it starts with a quadratic term here. So it's a degenerate critical point. These two guys have merged into one. Sorry, in the mechanical example, this fellow is a center and that guy is a saddle point. And these two have merged into each other, and you end up with no root at all. And all of a sudden, a stable and an unstable root emerge from nowhere, and a bifurcation has occurred. That's the simplest bifurcation you can think of. It's also called a tangent bifurcation, or a saddle node bifurcation. But the mechanism is clear. This sort of equation has no root, and then suddenly it develops plus or minus root. But it's nice to see geometrically that the cubic curve develops a sort of kink, an inflection point, and then that this higher order critical point separates out into a maximum and a minimum. The next in this order, in this progression, is x dot is p, and p dot is mu x minus x2. Yeah. Highly non-linear. Yeah, if it's a linear potential, nothing is going to happen. Yeah. As it crosses, nothing is going to happen. So it has to have higher order terms, at least a quadratic term, as you can see. So what will, yeah, at least a quadratic. I mean, the potential must have at least a cubic term so that you have more than one maximum and minimum possible. So you could ask, okay, why am I taking these simple polynomials? That's what people who study catastrophe theory and so on do. They take various polynomials here, generic polynomials, and unfold it and see what are all the possibilities. That's what they've done, but I've translated that into language of some particle moving in a potential. This kind. Now what's the V of x here? V of x would be equal to minus mu x squared over 2 plus x cubed over 2. Same as that, except that this is a quadratic term now. So this. And now what are the possibilities? Once again, let's plot for mu less than 0, equal to 0, greater than 0. For mu less than 0, this is parabolic upwards at the origin, and then this goes off to infinity. So it's a curve. It does this and goes away. But when you go to larger negative values of x, this is going to dominate, and therefore this curve has no choice but to come down. At mu equal to 0, of course, you have this curve where these two guys are merged. And for mu greater than 0, it's an inverted parabola near the origin, but eventually the x cube dominates in this. So the picture is immediately clear what's going to happen. The roots of this thing, critical points, CP is at p equal to 0, x equal to 0, and p equal to 0, x equal to mu. There are two critical points. This is the root at mu, and it's unstable as long as mu is less than 0. The root at 0 is stable. On the other hand, for mu greater than 0, the root at mu is stable, and the root at 0 is unstable. So its potential is shifted. So it's clear what sort of bifurcation this is. Exchange of stability bifurcation. This is the one we discovered yesterday. So again, x critical point versus mu. Now you have two of these guys, but I draw the unstable branch with the dotted line. So for mu less than 0, this root at mu is unstable, and then it becomes stable, whereas the origin becomes unstable for mu positive. And this is the exchange of stability. Bifurcation at mu equal to 0. There are only 3 elementary bifurcations of this kind. Yeah? This one, this thing here, mu equal to 0 is always an equilibrium point, a critical point, x equal to 0. But for mu less than 0, this guy is stable. It's a minimum of the potential. But the moment mu becomes greater than 0, this becomes unstable. And so I draw it with a dotted line. On the other hand, the root at x equal to mu, that root for mu less than 0 is unstable. So it's a dotted line. And for mu greater than 0, this is the point mu, it's stable, so it's a full line. These two guys come, merge, and they exchange stability. This is also called a transcritical bifurcation. So this is just so that you have familiarity with the name, or tangent bifurcation. This is exchange of stability or transcritical. And the last of these elementary bifurcations is this thing here. It's mu x squared minus x cubed. Sorry, mu x minus x cubed. This is mu x minus x squared. The next one is mu x minus x cubed. And what does the potential look like in this case? Just the integral of that. So this is mu x squared by 2 plus, sorry, minus mu x squared by 2 plus. That's the potential. Again, mu less than 0, mu equal to 0, and mu greater than 0. This potential V as a function of x. For mu less than 0, it's a normal parabola, and then x4 makes it go higher, so it's parabolic at the origin in this way, with a simple minimum at the origin. At mu equal to 0, it's a third order minimum. It's a very flat curve. Here. And for mu greater than 0, it's an inverted parabola near the origin, and then the x4 term provides stability. So it's a symmetric curve, and it's our familiar double well potential. So the critical points are at the zeros of this guy, which is at x is equal to plus or minus square root of mu for mu positive, and x equal to 0 is always a root, except it becomes unstable for mu positive. So this is root mu minus root. And they're both stable. And the middle guy is unstable. So the critical point, the bifurcation diagram, x critical point, now looks like for mu less than 0, 0 is a stable equilibrium point, always. So this is always the root for all mu less than 0. And as soon as mu becomes greater than 0, it becomes unstable here. So that's followed by a dotted line. On the other hand, two new roots, both of which are stable, have developed and have come out of the 0 and move out like a square root. So you have this, and you have this, and this is root mu minus 1. Since this picture looks like a pitchfork, it's called a pitchfork bifurcation. And this picture is familiar to you because this is, if you flip it the other way, this is exactly what happens to the spontaneous magnetization at a second order critical point, at a phase transition point, where at the critical point where you have at Tc in the temperature non-zero values of the spontaneous magnetization below Tc and 0 for the paramagnetic phase. So what happens there is a Pitchfork bifurcation. As you know in the Landau picture, the free energy is imagined to go through a sequence of changes of shape in this fashion. So these three are the elementary bifurcations. Now you could ask, what about, these are generic. You could say, why didn't I have x to the 5 here and x to the 7 there? You could, but they're not generic. They're essentially the same type of thing. And that classification, to show that these are the only ones, there's no new thing, requires a little bit of mathematics, which I'm not going to go in here. But that's what was originally addressed in this subject called catastrophe theory. And today it's a very well studied subject. People have classified all possibilities, and these are the most elementary possibilities. There's one more elementary four-dimension one bifurcation, which takes place genuinely in a two-dimensional phase space. This thing here, the phase space is essentially one-dimensional because P didn't play a role. I could just have put x dot equal to these guys here and looked at an overdamped case, but just to make it clear that there's a mechanical example, I use this. But the last one is again based on two-dimensional phase space. So let me use the symbols x and y for it. It goes like this: x dot, y dot equal to a linear function on this side, which is of the form mu x minus y, and then x plus mu y. These are the linear terms here. And you can see what this is going to do. I'm going to add nonlinear terms to it. This is going to be, the linear matrix is mu minus 1, 1, mu. This is the L matrix. The eigenvalues are mu plus or minus I. So lambda 1, 2, mu plus or minus I. When mu is positive, this would mean an unstable spiral point at the origin. When mu is negative, it's an asymptotically stable spiral point. So at mu equal to 0, I expect something to happen. For that, I need the nonlinear terms. So let me put a minus x times x squared plus y squared here. And this is the textbook example. Minus y times x squared plus y squared. Now look at what happens for mu less than 0. And now we need to put not just x versus mu, x critical point, but x, y, and mu. So let me imagine there's a y coming out here. This is mu. That is x. The stationary, if you like, the steady state or whatever, the analog of something like no time dependence occurs at all, but except it will happen in the radial variable. Now look at what's going to happen for mu less than 0. It's best to look at this in polar coordinates, so let's do that. R dot is x dot plus y dot. R squared is x squared plus y squared. So what does that do? This is going to give me an r squared when I add up these two guys with a minus, and then there's another r squared, so it's minus r4, and this will give me this, and this is going to be plus mu r squared. So it's r squared times mu minus, and these two terms cancel. You can adjust it so that they cancel. So it immediately implies r dot is r minus this. Now for mu less than 0, it's clear that R dot is always negative. So wherever you are in the plane, the radial variable is going to go towards the origin. And indeed we know that 0, R equal to 0, namely the origin x 0, 0, is an asymptotically stable spiral. Wherever you are, everything falls into x equal to 0, y equal to 0. So this. On the other hand, for mu greater than 0, the sign of r dot depends on where r is. So for mu greater than 0, r dot greater than 0 if r less than mu and less than 0 if r is greater than mu. Pardon me? Ah. So it implies if you're very far away, you're going to fall in. If you're very close, you're going to fall out. Clearly, if r is exactly equal to square root of mu, then this vanishes and r doesn't change, which means the system is going to go around in a circle in the xy plane. So there is this sort of, it's a kind of three-dimensional figure. There's a surface, and the radius of this is equal to square root of mu. And you can show it's stable. In other words, all points outside will flow into it, all points inside will flow outward towards it. And indeed, what happens to this spiral point is that it becomes unstable, as we saw. So this becomes a dotted line. And we have now a bifurcation at mu equal to 0. To the left of it, there's an asymptotically stable spiral point. Everything falls into it. To the right of it, that spiral point becomes unstable, and there is an asymptotically stable limit cycle. An isolated periodic orbit, which in this case is a circle, with radius square root of mu. An isolated periodic orbit is called a limit cycle. It occurs only in dissipative systems because there's always some shrinkage of volume or expansion involved. Everything from outside, larger values of x and y, collapses into it. Everything inside falls into it. So that's the stable attractor. This bifurcation is called a Hopf bifurcation. And this thing here is a stable limit cycle.
So does this also give me does this kind of thing also give me a prescription?
Yeah.
Finding if in a certain region I have a limit cycle, at least
finding all the limit cycles of a system is highly non-trivial. This is a simple
at least
example.
one. If I have at least one limit cycle in some region, that I can find it.
There's no angle. See, normally the dynamical system, the nonlinear system, is very complicated. It doesn't have this neat radial symmetry or anything like that. So discovering it is done numerically. There's no simple way of actually finding this. Well, by the way, the first limit cycle in physics was found in the context of what's called the van der Pol oscillator, when they were playing around with this generation of forces in the integrated circuit, VLSI generation. But in the old days when electronics started, they had these valves, vacuum tubes. They still have them in microwave ovens and so on. But they had these diodes and triodes and pentodes and things like that. And there was an oscillator circuit. One of the first circuits that was created was an oscillator circuit by van der Pol, named after van der Pol. And the equation for that, the evolution equation in the van der Pol oscillator, involved a nonlinear term. It was like a harmonic oscillator. There was an x double dot term, then plus an x dot term. But this x dot term didn't have a friction constant which had a fixed sign, but had something like 1 minus x squared multiplying it. So if x was less than 1, this acted in the right direction as friction. If x was greater than 1, it gives another feedback, etc. Or maybe the other way about. So this nonlinear system in the x dot plane turns out to have a limit cycle. And that is what one aims for. That is an oscillatory motion, which is what is stable. And that's how limit cycles were initially discovered. But after that, there's been a lot of progress in classifying limit cycles of various kinds. But there's no general algorithm for an arbitrary dynamical system to say where are the limit cycles, etc. Yesterday I mentioned the Bendixson criterion, which says that if this vector field f which we wrote on the right hand side, had a divergence that in some region had a fixed sign, then in that region no closed orbit was possible. By Stokes' theorem, we saw this explicitly yesterday during the tutorial. So criteria of that kind are known, but no general prescription as such. So the discovery of limit cycles is a complicated job.
So, but then that will mean, just by the Bendixson criteria, that will mean if I have a vector field with a certain sign in some region and a vector field another sign in a different region, there is a limit cycle, at least one limit cycle in the middle, right?
Yeah, there are general theorems which will tell you that it's either a limit cycle or some other kind of attractor. It could be another attractor altogether, like a strange attractor. Or it could be a generalization of a limit cycle, like a limit cycle is a one-dimensional object. It could be a toral attractor. It could be a torus of some dimensionality in between. So there are all these possibilities, including strange attractors in between. So you can't immediately say, except in the simplest cases. I'm not sure if everybody was present during the example that I gave or the mention of the Bendixson criterion. The statement was very simple. If you took just the two-dimensional case, for instance, if you have x dot is f of x comma y, just to repeat that, y dot is g of x comma y. If in some region you have a closed orbit of this kind in phase space in the xy plane, then it implies that on this orbit, it immediately follows that dy is dy over dx times dx, of course, but dy over dx is g over f dx, which implies that f dy minus g dx is 0. And you integrate this over this closed contour C, the closed phase trajectory C. So you have this C. This must be equal to 0. On the other hand, by Green's theorem in the plane, taking into account this minus sign as well, it's clear that this must also be equal to an integral over the surface, delta f over delta x plus delta g over delta y dx dy by Green's theorem. But this is the divergence of the vector field, which gives you the phase space velocity, the vector field f vector. And if this has a fixed sign in some region, then this integral can't be 0. So it violates the requirement that it be equal to 0 on this closed trajectory, which in turn tells you that the closed trajectory of this kind is not possible. That's the Bendixson criterion in its simplest form. And I applied this to the case of the Duffin oscillator, the one with the cubic term and the wrong sign for the linear term, and showed that in the presence of friction, you cannot have a stable limit cycle. You can't have a limit cycle period in this system.
Previous question, the divergence of your changes sign.
Yeah.
And at some point it has to be.
No, it doesn't have to go into, it doesn't have to, limit cycles come in various varieties. So this, if this is a limit cycle, it could be stable, unstable, semi-stable, things could fall in from one direction, fall out from the other direction, and vice versa. All possibilities exist. In particular, in higher dimensional spaces, you could have attractors which are not limit cycles, but which are like tori. So the system can fall into it or fall out of it, etc. And there could be strange attractors, which are fractal objects, into which everything falls. So it doesn't immediately, just saying, looking at the divergence of f doesn't tell you very much.
Any particular distribution?
Pardon me?
Any particular distribution, special distributions which causes the limit cycle?
Any particular?
Distributions or special distributions which causes the limit cycle in the system?
Yeah, in a crude way, yes, from the van der Waal. You expect that if, for instance, the dissipation term, the friction term, changes sign, exactly as he said, the dissipation part of it changes sign, then I expect that it's possible to have a limit cycle.
How many limit cycles in the system one can have? Is there any particular clearance of?
No. Look at this example. Again, sort of a hypothetical example. Look at r dot equal to sine pi over r. It's clear that if r is equal to r equal to what? 1 over n. If r equal to 1 over n, then r dot is 0 and I adjust theta dot appropriately, then it's going to be a circular limit cycle at the value 1 over n. And they will alternate in stability, as you can see by Taylor expanding this about the point r equal to 1 over n. The limit cycles will be stable, unstable alternately, and they have an accumulation point. So there's a limit cycle at n equal to 1,